Hey guys, we're going to pick up in this video where we left off yesterday, and we're going to be looking at predicting products with single replacement reactions, double replacement reactions, and combustion reactions. If you look on your reference sheet, on that same page we looked at yesterday that's next to your formulas list, for single replacement reactions, you're given this base formula of A plus BC gives you AC plus B. Remember we said you have an element and a compound, and the element by itself is trying to switch with an element in the compound. Here we have where a metal is replacing the metal in a compound, so A and B are switching places. If your compound is water, you can have a metal replace a hydrogen from water. So that will make the metal hydroxide and then hydrogen. You can also have a metal react with an acid, where yet again the metal and the hydrogen are switching places. So it makes the metal with that anion and hydrogen. If the element by itself is a nonmetal, it is going to switch places with the nonmetal that is in the compound. So here D and C are switching places. Let's look through some examples. Or actually, we'll come back to examples in a moment. Single replacement reactions do not always occur. So we do have to look at when we know these are going to happen. So remember, single replacement reactions always have an element and a compound on both the reactant side of the equation and the product side of the equation. To determine if a metal is going to replace another metal in a compound, you have to look at their reactivity. The metal by itself has to be more reactive than the one in the compound to force it out of the way. So on the back of your reference sheet next to your polyatomic list, you actually have an activity series of metals. This lists metals in order of decreasing reactivity. So the metal by itself, it needs to be higher on this list or more reactive to replace the metal in the compound. If the metal that's by itself is lower on this list than the one in the compound, no reaction will occur. Up at the top of your reference sheet, there is also a list for halogens. The halogen that's higher can replace the one that's below it. But note that this list is on the back of your reference sheet. And it looks a little bit like this. Excuse me, not all of this would fit on the page. But up top you have lithium, which is the most reactive. And then as it goes down, it gets less reactive. So a reactive metal can replace any metal below it, but it cannot replace anything above it. So for example, if you look at iron, Fe, which is right here, it can replace copper. Copper's way down here on the list. It's actually off the screen. So copper is below iron. So iron can replace copper, but it does not work the other way around. Iron cannot replace something above it like zinc or calcium. So if those were in the compound, we would end up with no reaction. So let's look at how we're actually going to predict products. So once you realize that it is a single replacement reaction because you have an element and a compound. So once you know it's single replacement, you need to look at the reactivity series to see if the switch can actually occur. So remember that the metal by itself needs to be higher on that list than the metal in the compound. If it is higher, and it will switch places, you're actually going to switch them. And whenever you pull out an element by itself, if it's with the halogens and they're switching places, make sure to look out for those diatomic molecules. Whenever you're writing the product, make sure to crisscross and balance your formulas and then balance the overall equation. So let's look through some of these examples. And I'm going to flip back to the reactivity series if needed. So we have iron and lead 2 nitrate. So what's trying to switch places is the iron and the lead. So we first need to make sure that iron is above lead on that list. So we'll go back to our reactivity series. Oops, excuse me. So here's iron. Lead is below iron, so those can switch places. So when we switch places, lead will come out by itself, and then iron will go in with nitrate. Now here it did not tell you which charge the iron would take, so it's acceptable to say it's iron 2 or iron 3. I'm going to make this one iron 2 so it's easier to balance. So that will give a 2 on the outside, and that is actually a balanced equation, so we don't have to do any further. Let's look at our next example. We have chlorine and sodium iodide. So the chlorine, since it is a nonmetal, it's trying to switch with the nonmetal in the compound. So this is actually trying to switch with the iodide. Now, if you look at your halogens list on the top of your reference sheet, chlorine is higher than iodine on that list. So they can switch places. So iodine will come out by itself. But remember, iodine is diatomic, so there has to be 2 of them. And then sodium is going to pair up with the chlorine. And that's a +1 and a -1 when we crisscross charges. So those are our formulas, but we would need to go and balance the overall reaction from here. Let's look at the last one. We have calcium and water. So calcium's a metal, so it is trying to replace a hydrogen from water. This was one of those special circumstances that was listed out. And if we check, calcium is higher on our activity series than hydrogen, so they can switch places. And if you look at your reactions on your reactivity series, this would be part B, where you have a metal with water, so it will produce the metal hydroxide and hydrogen. So we're going to use that pattern when predicting products. Sorry, my screen's going a little crazy. All right, let's try one more time. There we go. I don't know what just happened with my computer. So we said that they will switch, and it will make the metal with hydroxide, so calcium hydroxide. Remember, calcium is a +2 charge, hydroxide's a -1, and it will produce hydrogen. And then we can balance our reaction from there. So let's look at double replacement reactions. Double replacement reactions, you had the basic formula of AB plus CD produces AD plus CB. So remember we said our metal ions are switching places. In a double replacement reaction, you might end up with a precipitate. Remember from Unit 1, these are solids that form during reactions. You might form some sort of gas like carbon dioxide. You might also form a molecular compound like water. All of those are possible. And these are going to occur, so you do not have to look at the activity series for double replacement. That is only for single replacement. So remember, our metal ions are going to switch places, and when you're forming new compounds, you have to crisscross your charges. and they tend to keep the same charge from one side to the other, especially with those transition metals. So in our first example, lead nitrate and potassium iodide, lead and potassium are trying to switch places. So lead will now pair up with iodide, and it was lead 2, and iodide's a negative 1, so it will be PbI2. And potassium is now going to pair up with nitrate. Make sure whenever you switch these that the metal is still in the front of your compound when you crisscross. So those are our products, and then we could balance the equation from there by adding a 2 in front of potassium nitrate and then a 2 in front of potassium iodide. Let's look at our second example. We have iron 3 oxide and hydrochloric acid. So here the iron and the hydrogen are going to be switching places. So hydrogen will pair up with oxygen, which is going to end up making water, while iron pairs up with chlorine, and iron had a charge of positive 3, so that carried over, so it's going to be Cl3. And from here, we can balance our equation. We have 2 irons on our reactant side, so we need 2 on the product side. That gives us 6 chlorides, so we need 6 on our reactant side. That gives us 6 hydrogens, so we need to add a 3 to have 6 hydrogens, which also gives us 3 oxygens, so now it's balanced. Let's look at our last example. We have hydrosulfuric acid and potassium hydroxide. Remember, this is one of those acid-base double replacement reactions, so it should always produce water and some form of salt. So hydrogen and potassium are switching places. Hydrogen pairs up with hydroxide, which makes water, and then potassium pairs up with the sulfide. Remember, potassium is a positive 1, sulfide's a negative 2, so it will be K2S. So we need to multiply potassium hydroxide by 2, and that gives us a total of 4 hydrogens, so we need to multiply water by 2 as well. So we said we'd come back to look at how you know that some substances are solid, or if you're predicting the formation of a precipitate. So remember, the precipitate is a solid that forms during the chemical reaction, most of the time using liquids. And you can actually predict the formation of precipitate using solubility rules for ionic compounds. On your reference sheets, these are right above your types of reactions. It says solubility rules, and then there's a column for insoluble, and there's a column for soluble. If it is in the soluble column, these will be an aqueous solution. So these are the ones that are going to have an AQ written after the substance. If it's in the insoluble column, it is going to precipitate and form a solid. Now, we're going to walk through some of these rules, but note that a lot of these rules have exceptions. Exceptions are always going to be the opposite of what the rule is. So if it's an exception to a soluble rule, that substance will be a solid. If it's an exception to an insoluble rule, that will be an aqueous solution. So we said whenever you're predicting products for double replacement reactions, make sure you switch those positive ions and then write the formulas for the new compounds by crisscrossing to balance the formula, balance the overall equation, and for double replacement reactions, you want to look at your solubility rules to see what will be a solid and what will be aqueous. And whenever you're looking for aqueous and solid, make sure to look at both products. It may be that both of them are aqueous, one of them's a solid, or both of them are a solid. Remember, transition metals tend to keep their charge from the reactant side to the product side. And make sure that you are crisscrossing your charges. Don't just assume that the subscript moves with the substance. The only time the subscript is going to stay the same is whenever you have that polyatomic ion, that the subscript is part of the formula for the ion. So let's look at our solubility rules. This is what is pictured on your reference sheet. One thing to note is they are organized by the anions, the nonmetals, with the exception of ammonium. Notice the headings. Pay attention to, is it in the soluble list or the insoluble list? And pay attention for exceptions. Your cations and metals are going to be listed as exceptions to rules. And we're going to go through some examples with these. But some things to note, anytime you have a nitrate, acetate, ammonium, or any metal that's in group 1, like sodium and potassium, it will always be soluble. There are no exceptions to the rule. But something like chlorides, bromides, and iodides are going to be soluble unless they're paired with silver, lead, and mercury. Those metals will make the compound a solid instead of an aqueous solution. If you're reading the insoluble column, carbonates and phosphates will always be insoluble unless it's group 1, like sodium, potassium, or ammonium, because those were always soluble. So remember, the exceptions are the opposite of the rule. Let's look at some of these and see if we can figure out if they are aqueous or solid. Let's first look at potassium bromide. So we want to look up the rule for bromide. So that's the second bullet under our soluble list. It says that bromides are soluble except silver, lead, and mercury. Potassium is a group 1 salt, so it's automatically aqueous. But you could go based off of your bromide rule or your group 1 rule. Let's look at lead 2 chloride. We want to look at the rule for chlorides. Yeah, my computer's being slow. So chlorides are soluble, so aqueous, but lead is an exception. So it's going to be the opposite of the rule. So that will end up being a solid. Let's look at the next one. We have potassium hydroxide, so we want to look up the rule for hydroxides. Hydroxides are on our insoluble list, so it's solid, except group 1, strontium, barium, and ammonium. Well, potassium is in group 1, so it's an exception to the rule, so this will end up being aqueous. Let's look at silver carbonate. So we want to find our rule for carbonates. Carbonates are insoluble, so solid, except for group 1 and ammonium. Silver is not in group 1 or ammonium, so it will be a solid. Now our last one, we have iron 3 nitrate. If you look at that first rule on your soluble list, all nitrates are soluble, so this will be an aqueous solution. So remember, whenever you're looking at these solubility rules, you want to pay attention to that anion that shows up. Oops. Yeah, I'm not sure what happened right there. I'll move that out of the way. So our last type of reaction is combustion. So remember we said that combustion always has oxygen as a reactant. If it's just an element with oxygen, it's going to react like a synthesis reaction. But where we have these true combustion reactions that follow the pattern on your reference sheet, it tells you have a hydrocarbon, so something with carbon and hydrogen plus oxygen always produces carbon dioxide and water. And then you would have to balance it from there. Remember, these are the ones that can be kind of tricky to balance, but it is not hard to predict their products. This is where we're going to stop in this video. I'm going to make a video going through some other examples. Feel free to check that one out.